I'm going to try to work through this example that I started but did not finish in class. It says the amoeba sits on a frictionless ramp at a given angle with respect to the horizontal. The ramp has a mass of 5 nanograms, and the amoeba has a mass of 1 nanogram, and they accelerate together at a constant acceleration a in the x direction. This turns out to be the secret to the problem, because I can write down for this xy coordinate system, I know that the acceleration in the x direction is just going to be a constant value for all the bodies in the system, and the acceleration in the y direction is going to be 0. And that's going to be what allows me to solve the problem. So good reading there, Eric. Next, we're going to go ahead and write down the ramp. Free body diagram. It's a little complicated, so forget that. Let's do the amoeba. And if anything, this example has taught me how to spell amoeba reliably. So amoeba has 2 forces sitting on it. The weight of the amoeba, which is ma times gravitational constant. And then we have the normal force from the ramp that's pushing up on it. And because the ramp is a live part of the system, I want to go ahead and say that that's a force of the ramp on the amoeba. And I can even go ahead and identify the angle theta in my diagram here. That's going to help me with my decomposition. Again, I usually just say the angle theta is going to go to 0, so this vector in that case would then line up and be opposite direction of the weight. Beats doing trig any day. Just think about it instead. So then what I can do is input my forces on the free body diagram for the ramp. It's got a force pushing on it. That's given in the problem. We have a weight, the mass of the ramp, times g. And finally, we have the amoeba pushing on the ramp. And like all of these problems, we have a force of the amoeba on the ramp. Finally, I should say finally now, because there's also the normal force from the Earth, and since the Earth's not going to be moving in my problem, I'll just call that n, and really hope I don't have to deal with it. So let's go over here and start writing down some relationships. Well, first, I know from Newton's third law that the force of the amoeba on the ramp has the exact same magnitude of the force on the ramp on the amoeba. And remember, what we're doing here is we're saying the magnitudes are equal, and we are keeping track of the opposite part of Newton's third law through the arrows and making sure we do the decomposition correctly. Now, just like when I consider the limit of this angle going to 0, this angle here would close up. It's this angle in the drawing here that would close up, and then I can get a hint on how to do my decomposition of that vector. So from there, I'm going to call this equation 1, because I'm going to get a lot of equations. So let's consider the amoeba and start writing down Newton's second law. So start with the third law wherever possible. Figure out your pair's forces, and then resort to F equals ma. So if we consider the x direction, let's get going. For the amoeba, that gives us the mass of the amoeba times the acceleration. Remember, the acceleration in the x direction is given up here, and that's equal to the sum of forces. Look up here. So looks like that force is going to run off in the, it's a sine theta. And so this one's got to be the cos theta. Okay, so in the horizontal direction, this acceleration has to be provided by F R A sine theta. That's pretty good. Let's move on to equation 2. In that case, it's the sum of the forces in the y direction. We know that they're 0 because that's ma times the acceleration in the y direction. We know that's 0 from the givens in the problem, so let's get going and say, all right, I can decompose that, and I get F R A cos theta. Genius. And that's the force in the up direction, so I better write down the force in the down direction, which is ma times g. Whew, this looks like a really good equation for getting rid of the force in the RA in terms of known things in the problem. I like that. Okay. Did I say that was equation 2? Because I was filled with lies. That's 3. Because now I need sweet, sweet equation 4. So moving on, I'm going to say the sum of the forces in the x direction is going to be on the ramp. Let's be clear about where we're going here. Force of the equations in the x, the sum of the forces in the x direction, totally can speak today. Oh, it's too late. Mass of the amoeba times the mass of the ramp times the acceleration. Okay, that's for the ramp. I just like saying amoeba, that must be it. And then I can go ahead and do the decomposition here. Well, look, here's a force going off in the positive x direction. F. And then we're going to subtract from that the component of the force of the amoeba on the ramp in the negative x direction. See, it's pointing backwards with respect to my x-axis, so that means it gets a big old honkin' negative sign. So that's force of the amoeba on the ramp times, looks like my trig says, that's the sine of the theta. So hey, there's an equation. Looking good. And then finally, I get equation 5, which secretly I won't ever use, but I could write it down anyway. The reason why I'm not going to use it, well, it's 0, and it introduces a variable I don't really care about, which is the normal force from the Earth on the ramp. And just to be a good citizen of physics, I'm going to write that's mr times g, that's the weight. And the amoeba on the ramp has a component in that direction too. So FAR cos theta is in that direction. So we could use this to solve for the normal force, should somebody care about it. Turns out I'm not that kind of person. So let us go ahead and solve equation 3 to get rid of my FRA. So I can go ahead and say, well, this equation is going to give that FRA is going to be equal to MAG over the cosine of theta. Now, technically, I think I know all of those, but I'm going to resist my temptation to plug in numbers now because I don't like suffering. So what I can do is take this relationship, so this is solve 3, and then we're going to go ahead and use equation 1 and 3. We're going to plug those into 4. And what's going to happen is I can say, well, I've got an expression for the force of the ramp on the amoeba. That's equal to the force of the amoeba on the ramp. And then I can go ahead and come down here and sub in this expression. So then I get that the mass of the ramp times the acceleration is equal to the force minus, and now here comes the equation 3, mass of the amoeba times g over the cosine of the angle times, that's FAR, and that's equal to sine theta. Check it out now. So we have our constant force. Looking for this? Hello, we're looking for that. Okay, so then we can solve for that. So let's solve this for F. F is equal to mass of the ramp times the acceleration plus the mass of the amoeba times g times tan theta. Okay, so right here we've used 3, we've used 1 and 4, and I've got this acceleration here. It's not given in the problem. I've got one equation left. Help me, equation 2. You're my only hope. So I'm going to take equation 2. I'm going to solve this for the acceleration. And that means that the acceleration is equal to F of the ramp on the amoeba divided by the mass of the amoeba times sine theta. Know these two things. Do I know FRA? Yeah. Let's go pull that from this solution. It's like right here, staring at me. Okay? So that's equal to the mass of the amoeba times g over cos theta times 1 over the mass of the amoeba times sine theta. And that, do some canceling. Goodbye, amoeba mass. And sine over cos becomes tan, so we just get g tan theta. It's kind of familiar, so we can plug that up right there. And we get that the force, so these things together mean that the force is equal to the mass of the ramp times g tan theta plus the mass of the amoeba times g tan theta. And then I can go ahead and factor things out because I'm cool. I'm going to say g tan theta times the mass of the ramp plus the mass of the amoeba. If you plug in your numbers that are given in the problem, mass of ramp is 5 nanograms, mass of the amoeba is 1, theta is 30, g is 9.81 meters per second squared. My calculator, good old trusty Huey, tells me that the answer is 34 nanonewtons. All right, I think that's what we wanted to do. So, hope that was helpful.